Hiya! So in this video, we're going to be starting to talk about vector products. In particular, what we're going to look at is trying to figure out the area of parallelograms or volumes of parallelepipeds, however you say that word. And we're going to do this in terms of vector or cross products. In other words, we're going to introduce a new product. Vector product. So as a quick recap, we've already seen two different products. So we've seen actually many different types of products. One is scalar product, right? And this was when we multiply some number by a vector, number and vector. We have normal product, so like just a standard normal product, and this is a number times a number. We had the inner product, right, which we denoted by this, and this is a vector times a vector. And now we're going to define another product. And this we're going to call the vector product, not to be confused by the inner product. I guess there's also, I forgot, matrix product. So multiplication by matrices. And this is a matrix and a matrix. Etc. Now we're going to define something called the vector product, and this is really going to be helping us for calculating area. So inner product kind of helped us with lengths and angles. Vector product is really going to help us with areas and volumes and stuff like this. So you can kind of think of vector product as multiplication of vectors, whereas the inner product is more like, in some sense, you're just like seeing things how they work together, like how far apart, how long things are, what angle they rotate, etc. So it's not it's a little different. So vector product, all it is, I'm actually used to it as a cross product, so you'll often probably hear me calling it the cross product. And this is because this is given by the map something cross something else. So here it's fairly, you have to start noticing, well, I'll mention this in a minute, but one thing, or I guess I'll mention it now. One thing to know is this cross here looks very similar to an X. So normally when I write X's, right? So if I take this and I write it out, notice how when I write my X's, I put them almost as two C's. This is different than my crosses, which look like a normal X. So these are little things that we'll have to pick up. But just note that the way I write my X's and the way I write my crosses are different. So this should help notation-wise. And I would say it might be a good idea to start doing that difference as well so that you can kind of see the differences. So we want it to satisfy the following properties. So remember how with the inner product, we said it has to satisfy these things. With the vector product, we want it to satisfy the following properties. So first one we want to satisfy is that the vector x cross y is orthogonal to x and y. So what this is saying is this vector has to be orthogonal to both x and y. So they all have to be just equal to 0. So that's one point we have. The other thing we want is anticommutativity, which is a very fun word. And what you're probably used to seeing is, so normally when I multiply things, right? So in normal multiplication, x times y is equal to y times x. And we saw that with the inner product, right? If I take x times y and y times x, these were all the same. But for the vector product, we want anti-commutativity, which basically means I want to pull a minus sign in front whenever I multiply. In other words, if I switch the sides, then I need to keep track of a minus sign. This is going to make minus signs very difficult to keep track of, in the sense that, you know how you used to make a million minus sign errors? It's only going to get worse. So make sure you double check minus signs 6 million billion times. The other thing we want, kind of as we've seen before, we want to keep this idea of linearity. So we always want something linear. So in other words, we want lambda x plus mu y, right? So if we want this to be linear, and I cross product it with z, I should just be able to pull out my x and z plus mu y cross z. Yeah. Another thing we want is to keep track of the length. And what we want is whenever x and y are perpendicular, right? So whenever they're perpendicular, remember we have this equality, perpendicular. Then the length of the vector product has to be equal to 0. In other words, what I want is the length of the vector product has to be equal to 0. Or sorry, has to equal the area. I was looking at the wrong one. Has to equal the area of the rectangle formed by x and y. So in other words, if I have two things, right? So I have x and y that are orthogonal. Then I want x cross y to give me this area. And the last thing we want is that for any linearly independent vectors x and y, the basis given by these three has the same orientation as v and y. Now here, the key thing to note is this is an ordered basis, right? So x and y, x comes before y, and then we have x cross y. So x, y, x, y. Yeah. So this is important for that. So also, as with the inner product, so same as the inner product, we can use anticommutativity of the inner product together with linearity to actually show that it's linear in the second term. So here we're basically doing that. Here I use anticommutativity, anticom. Then I use linearity in the first term. Now here, I'm keeping track of my minus signs because when I come back, I have to flip the signs again. And so here, this is just anticommutativity again. So even though we have anticommutativity, we can do this in the second term and it doesn't matter. So in other words, this is actually a bilinear kind of thing. So a couple remarks while we're here. So we have one that it's bilinear. The second remark is that anticommutativity also means that if I take the cross product with itself, it has to equal to the minus sign. So the self product is always equal to 0. Always. So x cross product x is 0. Furthermore, we have something a little more, that if x and y are not linear independent, so if something is not linearly independent, that means y is going to be some scalar multiple of x. Then the product x cross y is going to be equal to, so let's figure this out. So x cross y, this is x cross lambda x, which is lambda. We can pull the lambda in front. X cross x. And this is just equal to 0, right? So lambda times 0 is equal to 0. So in other words, if x and y are not linearly independent, there's some lambda where this is just gonna go to 0. The second part is by which axiom is this? By the orthogonality axiom, right? So this was up here, this first kind of one we saw, that they're orthogonal to x and y. We have in particular that x cross y is perpendicular to this plane spanned by x and y. So this is why we know that the x, y, and x cross y gives us a basis. So this is in particular where this is coming from. So we don't have to show it's a basis. This is given to us. What we had up here, we didn't say that, oh, they have to be a basis. What we said is, we know it's a basis from the previous things, but it has to have the same orientation. That's the key part for that one. And the final remark, I guess I should note these down. So remark here is the bilinearity. The remark here, what's the important part, is the self product is always 0. 185 is that this gives us a basis all the time. So what's remark 186 saying? That the orientation of V is actually important. So remember how I was kind of saying that X and Y and X cross Y, they have to be done in that way. So in other words, if Y is the oriented vector space that contains the same vector space as V, but comes with opposite orientations, then for the vectors X and Y, the basis X, Y, X cross Y has the same orientation as V by the previous axiom. And this basis has the opposite orientation to W. And hence the vector product on W would give a vector in the opposite direction, but it's still going to be perpendicular to X and Y. So I said a lot of words. Let's kind of, this is 3 dimensions, so it might be a little harder to see. But if V is given by X, Y, and X cross Y, and here we can kind of look at an example where W I set as the opposite one. We'll just switch these two. Oops, no line there. So this, yeah, sorry. This is V, and this is Y, right? Yeah. Has the same orientation as V. Wait. Yeah, okay, whatever. This was right before. Because we just take any of them, so it doesn't matter. So V is going to have the same orientation as X, Y, X cross Y. W is going to have the opposite because we flipped the order of the first 2 vectors. So it's going to have the opposite orientation. In other words, the vector product on W is going to give a vector in the opposite direction. In other words, if I look at Y cross X, right, this is equal to minus X cross Y. So it's the vector in the opposite direction. Vector in opposite direction. So it's really just talking about this anticommutativity, but in a little more general sense, where here we're letting V be anything. Here, V is any basis, and W is any opposite basis, right? So this is the kind of key part. Here we chose specific ones, but V and W can be anything. I'm now babbling. Oh my god, this video is hella long. All for a definition. So we'll stop here. Sorry, this definition is long. And I'll see you in the next video where we talk about this a little more. Sorry about the long video. Bye.